Okay, cool. So now we have 3.2, which is compound interest. So the way compound interest works, again, is if you put in $1,000 every month, let's say you put $1,000 in every month, and it's compounded either daily, weekly, monthly, over X amount of years, then what compound interest does is tells you how much money you would have if you kept doing this over that span of time. So it's definitely way better than simple interest theorem, because simple interest theorem says, hey, you put in $1,000, that's it. You wait 20 years, let's see what you have. But compound interest says, hey, you put in $1,000 every week or every month over this amount of time, over this interest rate, over this many compoundings. And compoundings mean how many times a year. So if you compounded daily, weekly, monthly, it's going to tell you how much money you have at the end of this time period. So compound interest is definitely way better than simple interest theorem. So with the example here, it says, all right, so we are using simple interest theorem to calculate. I put $1,000 in after 3 months, and then I put another $1,000 after 6 months, and then I put another $1,000 after 9 months. So we see how our money's rising. So instead of having to always calculate every investment every time you put in $1,000, why not generate a formula that will do that for us? And this is where compound interest comes in. So the compound interest formula summed up says, all right, well, your final amount of money, A, so your final amount of money, A, will be given by the initial amount you put in times 1 plus the rate you're given over the number of compoundings raised to the number of compoundings times time. So this is going to tell you how much money you will be making at the end, again, of a certain period of time. To sum it up, if you want to make the formula look fancy without all those letters, then you can write it as A equals P plus 1 plus I to the nth power, where I is your rate over compoundings and N is compoundings times time. So it just puts the formula in a simpler format for you. Okay, so for now, let's go ahead. Let's see. The example below says solve the compound interest for P, N, and T. Okay, so let's go ahead and work with this formula then. All right, so we're going to be rearranging this compound interest formula. So I'm going to rewrite it here. So A equals P times 1 plus I to the N. And remember that I is rate over compoundings and N is compoundings times time. Okay. So first up is solve this formula for P. So we'll say A, solve for P. So given A equals P times 1 plus I to the N, in order to solve for this P, we just divide by 1 plus I to the N. So divide this by 1 plus I all raised to the N. And we get that our new formula is A over 1 plus I to the nth power equal to P. So this will help us solve for P. Okay. And then B, let's go ahead and solve for N. Okay, so using the same formula, A equals P times 1 plus I to the N. Our goal is to solve for this N. This means we have to figure out how do we take that N and bring it down. How do we take that n and bring it down? So the only way to do that is by using something we learned last class, and that is by using logs. So remember that if I have the natural log of x to the nth power, then I can rewrite it as n times the natural log of x. This is the power rule for logarithms. So what this means is that in order to solve for n on this equation, I have to apply the natural logs to both sides of this equation. So this is going to look like this. The natural log of a is equal to, or actually, should I apply it just yet? No. I have to get rid of that p first. Sorry. So first thing we're going to do is divide by p. Don't worry. Don't have to erase anything. So this will be the natural log of a over p. So we just divide that p. And then I'll have the natural log of 1 plus I all raised to the n. Okay, now by the power rule for logarithms, this n is coming to the front. So what we have now is the natural log of a over p equal to n times the natural log of 1 plus I. So now, in order to solve for n, we just divide by the natural log of 1 plus I. Use a different color. So we divide by the natural log of 1 plus I. All right, and now our new formula is natural log a over p over natural log 1 plus I equal to n. Too crazy, right? Okay. So that's how you solve for n. And now the last part is to solve for t. So C, solve for t. Okay, well, here's where we're going to pick up at. We're going to start where we left off on B, because remember, n is equal to mt. So here's how we'll start this off. N is equal to the natural log of a over p over the natural log of 1 plus I. But again, remember, n is mt. And you get mt equals the natural log of a over p over the natural log of 1 plus I. And in order to solve for time, all you have to do is divide by m. And if I divide by m, you will get t equals the natural log of a over p over m times the natural log of 1 plus I. All right. And there's actually one more formula we can make for this. And it's just going to be solve for m. We're going to start right here. You have mt equal to the natural log of a over p over the natural log of 1 plus I. And if you divide by t, m would equal the natural log of A over P over T times the natural log of 1 plus I. There you go. So reference these formulas and know how to use them. So one solves for P, the other solves for N, and the other two solve for time or M, which is compoundings. Okay, so you have all four of those rewritten. We rearrange them, so save those, reference those, and you won't have to rearrange them ever again. Okay, so the next examples is let's use these formulas to help us solve or simplify the given examples. Okay. So number one, P is 2,550, I is 0.07, and N is equal to 27. So for this one, we are simply just using A equals P times 1 plus I to the nth power. So they're giving us everything we need to plug in to help us solve for A. So here, A would equal 2550 times 1 plus I, 0.07, all raised to the 27th. Okay. So now, plugging this into Desmos, I get a clear calculator. Let's see. There we go. Well, type it like I wrote it. 2550 times 1 plus 0.07, all raised to the 27th. And you get 15,845.36. Okay, there we go. Not bad. Once you know the formulas, it's a lot easier to plug in. 2, A is 2,200, I is 0.069, N is 84. So this means we are looking for P. So we're going to be using this formula. P equals A over 1 plus I to the n power. Okay, so plugging it in, P equals 2,200 over 1 plus 0.069, all raised to the 84th. Let's see what we get there. Fraction, 2,200 over 1 plus 0.069, all raised to the 84th. And 1 plus, yeah, that's right, 8.09, so basically 810. Is that right though? 1 plus, yeah, into the 84, okay. 8.096, so 8.10. All right. That just seems too small. Did I miss a number? No. Let me see something real fast. No, that's right. $8.10. Okay, cool. Just had to make sure. Okay. And then 3, A equals 2P, I equals 0.11, and what is the value of N? So for this one, we're using that third formula, N equals the natural log of A over P over the natural log of 1 plus I. Okay. So plugging in what they're giving us, it has n equals the natural log, and a is equal to 2p. So we're going to get the natural log of 2p over p over the natural log of 1 plus 0.11. Well, 2p over p, your p's will cancel, and we get the natural log of 2 over the natural log of 1.11. So let's see what we get there. Natural log 2 over the natural log of 1.11. And this gives us 6.64. All right. So we have used 3 versions of the formula so far. We used the original, a equals p times 1 plus I to the n. We use the second one, p equals a over 1 plus I to the n. And third, n equals the natural log of a over p over the natural log of 1 plus I. Everybody good so far? Okay. Now 4. If $2,000 is invested at 7% compounded monthly, what is the amount after 5 years and how much interest is earned? Okay, so let's label everything we're given. So we want to know what is the amount after a certain amount of time. So again, we're using this formula. A equals P times 1 plus I to the n. So let's label everything we have. So we are investing $2,000. So that's P, our original amount. And then we are investing it at 7% compounded monthly. So this is where we fill in that I value. Remember that I is the rate over the number of compoundings. Well, our rate is 7%, so 0.07, and our compoundings are monthly. So when you compound, it's how many months are in a year. So when we say compounded monthly, it's going to be 0.07 over 12. And then n is the number of compoundings times time. Well, once again, we are compounding monthly, so that number will be 12, and we are doing this for 5 years. So 12 times 5, we get 60. Now 0.07 over 12, if it's a nice number, we will convert it to that, but if it's not, we'll leave it as that fraction. So let's see, 0.07 over 12, and no, we're going to leave it as the fraction, 0.0 over 12. Okay. Now plug it into the formula. A equals P, 2,000 times 1 plus I, 0.07 over 12, all raised to the 60th. Now let's see how much money we're going to have after 5 years. So I can type it in just like I wrote it. 2,000 times 1 plus 0.07 over 12. Close those parentheses. And then all raised to the 60th. All right, that was raised to the 60th. All right. And after 5 years of investing $2,000 at 7% compounded monthly, we will have $2,000 $835.25. And then it says, how much interest did we earn over those 5 years? Well, take our final amount and subtract it from the original amount invested. So interest is going to be that minus 2,000. And the interest is $835.25. Okay. Everybody go with that. Okay. So these formulas, I think I said we were putting in money every month, but no, that was a lie. These formulas say you put a certain amount of money in, and now better than simple interest theorem, because for simple interest theorem, it was you put a certain amount in, you get a rate over a year, that's it. With these formulas, you put that amount in at a certain rate, but now your money is getting compounded either every day, every week, every month for a certain amount of years. So now your money's making more money, and you will definitely make more money using compound interest than using simple interest theorem. So there we go. Okay. All right. So that is compound interest. Next is continuous compound interest. This says, hey, what if your invested money is making interest, is getting invested every second, every minute, every hour, every day for X amount of years? How much money do you think you would have? So this says, what if your compounding's headed towards infinity? So basically, what if they never stopped? What if your compoundings kept going? They kept getting increasingly larger. So what would happen to your A value? Well, we would assume that if our compoundings went on infinitely and our money increased and increased, we'd be super millionaires, billionaires, trillionaires. But no, unfortunately, it doesn't work out that way, because when we invest our money, we're only allowed to invest it at a certain rate and for a certain amount of years. And those amount of years are the time that we are alive. So no, we won't be billion trillionaires. We can hope to be, though. I hope I am one day. I hope you are one day, but we just have to have the money to do that. So here's how continuous compound interest was made. They said, well, what happens if if compoundings head towards infinity and A heads towards infinity? So they manipulate the compound interest formula. They manipulate the compound interest formula by raising everything to the R over T and then simplifying it, getting an expression such as 1 plus 1 over h to the h. Well, we saw this expression in exponential notes. Remember that this expression, 1 plus 1 over h to the h, will reach that magical number of e if h is headed towards infinity. So that's what we're assuming here, is that, well, if compoundings are getting infinitely larger, then money should do the same. Our interest should do the same. So this is where continuous compound interest is. So it may be more appealing to investors. So like, hey, instead of having your money work for you monthly, how about having your money work for you every second, every minute, every hour? And people like to hear that. But of course, there's caps on everything. But this is how the continuous compound interest formula was made. So after all that manipulation, we see that this whole expression becomes E, and we get continuous compound interest. A equals P times e to the RT as long as h heads towards infinity. So here's where that famous formula PERT comes in, used in a bunch of business models. So continuous compound interest. And of course, there is differences between investing with continuous compound interest and just simple interest. So if you look on the graph at the left, let's say that Here you put $1,000 in. Let's say it's like what is it? Those investing things called like CDs. They are the safest investment anybody can make, but you will make the slowest amount of interest over the years. But your money will never be harmed if the stock market crashes. So this is what that left graph would represent. Let's say I want to be real safe with my money. I put $1,000 in and I just wait. And you see that over the years, your money, your $1,000 at a certain interest rate is only growing at a linear pace. Look at those straight lines. You're like, yeah, it's cool. My money's growing. It's safe. It can't be touched, even if the stock market crashes. But now you talk to an investment company. They're like, hey, give us that $1,000. We'll give you a good rate. We'll compound it monthly and over a certain amount of time. Well, now look at what your $1,000 is doing. Your $1,000 is now a curve. So over the same amount of years at a different interest rate, your money is exponentially changing. Look at that. Even at the lowest interest rate of 0.4 or 4%. So I personally would rather have the exponential investment than the linear one. Yes, this is safe, but why not risk it, right? So that's what an investment company would show you. They would probably show you these two models of like, yeah, you can grow your money here. That's safe, but then why not give us more? We'll give you a better rate over a certain amount of time. And this is what your money will do. So of course, any normal person would choose the second graph. They're like, that's what I want my money to do. So this is why we have compound interest and continuous compound interest for those risky investors. And then they'll probably have a middle graph here where it's for moderate. You want to be safe and you want to be risky at the same time, but you don't want to lose that much. So that's money, right? Crazy, crazy. Okay. So one grows linearly, one grows exponentially. Now, we want to take that compound interest formula, PERT, and solve it for P, R, and T. So we want to take A equals P times E to the RT, and let's solve it for P, R, and T. So A, we're going to say solve for P. And here, A equals P times E to the RT. And all you have to do to solve for P is divide by E to the RT. And we get a new formula that A over E to the RT is equal to P. Okay. Next, solve for R, solve for T. So B, we'll say solve for R. And you have A equals P times E to the RT. Our goal is to get R down from being an exponent. But of course, that is going to use natural logs. So first thing we want to do is get rid of that P. We're going to divide by P. So if you divide by P, you get A over P equal to ERT. Now again, here's where we use the logs. We will use the power rule for logarithms again. So we apply the natural log to both sides of this equation. And we use the power rule. That means that this RT is coming to the front again. And we have natural log A over P equal to RT times the natural log of E. Now, this was also in the log notes the other day. The natural log of E the natural log of E, since the base of the natural log is E, the natural log base E of E will always, always be 1. So that natural log of E becomes 1. And what we are left with is natural log of A over P equals RT. And if you want to solve for R, all you have to do is divide by T. And we have our formula. Natural log A over P over T is equal to R. Which means you also have the formula if you want to solve for T. So C, we say solve for T, and we begin right here. So we begin at the natural log of A over P equals RT. And now if you want to solve for time, you divide by R. And you get natural log A over P over R is equal to T. There you go. One formula solves for P. One formula solves for the rate. One formula solves for time. And the original formula solves for how much money you would have at the end. So it solves for A, the final amount. All right. Whew, lots of talking. Everybody good? All right. And again, these formulas are rearranged. We just have to know how to use them. Okay. So next is use the continuous compound interest formula to find the indicated value. Okay. So this gives us P is 2000, R is 7.77, and T is 4. What is the value of A? So this is going to use regular old PERT. So just plug it into PERT. A equals 2000 times E raised to the 7.77. So remember, you always convert to decimal. So raise that to the 0.0777 times time. And of course, using Desmos, you can type it in just like I wrote it. 2000 E raised, and I would start a parentheses and do 0.0777 times 4. And we get 2,729 and 3 cents. All right. Next, 2. A is 19,565. P is 14,700 and T is 48. What is the value of R? So here we look for R, which is given by the natural log of A over P over T. So R is natural log A over P over T. And remember, time always has to be in years. So when we plug this into our formula, we'll have the natural log of 19,565 over 14,700 over T. And remember, since it's months, you have to convert it to years. And here, 48 months is actually 4 years if you divided that by 12. So I can even just leave it as a fraction, 48 over 12, which is just 4. Okay, now here's how we're going to type this in Desmos. So make your fraction button and then say natural log, parentheses, do another fraction and do 19,565 over 14,700, close that parentheses. And then down below, we'll just put over 4. And we get 0.071, which is 7.1%. Okay. Again, if you have any calculator issues, let me know. All right. And then 3, we want to solve for t. A is 89, 89,000. P is 62,326. R is 9.5. And we're looking for time. So that formula is T equals natural log A over P over R. Okay. So T is going to be the natural log of 89,000 over 62,326 over 0.095. Okay, now let's type that in. Fraction button, natural log, parentheses, fraction again, 89,000, 62,326 over 0.095. And we get 3.75. I assume that would be years. Okay. So again, that's just practicing the formulas for continuous compound interest. Everybody good? Okay. And then 4. If $2,000 is invested at 7% compounded continuously, what is the amount after 5 years? Okay, so again, here we will be using PERT, regular old PERT. We are given $2,000. Our rate is 7%, 0.07, and time is 5 years. And the reason we're using PERT is because of these words: compounded continuously. All right, so plug these in. A equals 2,000 times E to the R 0.07 times T. There we go. Let's see. 2,000 raised to the 0.07 times 5. And we have 2,838.14. Also, for your answer, I don't think I would put commas, because I don't think my math lab likes the comma. So I think when you're putting in your answers for these, just make sure there's no comma in there. You just put 2,838.14. Okay. All right. So now the biggest difference between knowing which formula to use: do we use compound interest or do we use continuous compound interest? And the easiest way to spot it is if a problem says you are compounding continuously. If it says compounding continuously, you will use PERT. If it says you are compounding over a certain amount of days, weeks, or months, you will use compound interest. Okay. Let's try it out more applications. All right. So a newborn child receives a $4,000 gift toward a college education from her grandparents. How much will the $4,000 be worth in 17 years if it is invested at 5.4% compounded quarterly. Okay, so you are compounding quarterly, which means we get to use the A equals P times 1 plus I to the n. This means we use the compound interest formula. Okay, so we want to know how much it will be worth. So this means we are looking for A. We know that her grandparents gave her $4,000. And then the rate they are receiving, actually, we don't have to do that. Remember that I is rate over compounding. So now the rate is 5.4%, so 0.054. And compounding, we are compounding quarterly. Does anybody know how many quarters are in a year?
Sir, 4.
4. Good. So 4. Okay. And then n is compoundings times time. So it would be 4 times time. We're doing this for 17 years. And 4 times 17, that is 68. Okay, cool. And now put it all together. A equals 4,000 times 1 plus I. And I don't think, let's see, 0.054 over 4. That's a nice number. We could use that. So hang on, let me erase that because it'll make typing it in your calculator a lot easier. So 0.054 over 4 is 0.0135. Now that's a clean decimal number I can work with. If you want to keep it as a fraction, you can still keep it as a fraction. Okay, but now A equals 4,000 times 1 plus 0.0135, all raised to the 68. And let's see what we have. 4,000 times 1 plus 0.0135, all raised to the 68. And after 17 years, this money will be worth $9,955.78. There we go. So in 17 years, that investment makes $5,955. That's okay. Not great, but it's okay. Again, that's why you always put more in. All right. Everybody go with that. Two, an investment company pays 3% compounded semi-annually. You want to have 20,000 in the future. How much should you deposit now to have that amount 5 years from now? So you want to have $20,000 in the future. How much should you deposit? Okay, so again, this says compounded semi-annually. So again, we're using the compound interest formula. So we're still using that A equals P times 1 plus I to the n. But this time it says we want to know how much should we deposit. So we're actually looking for P. Okay. So we know we want to have $20,000 in the future. This company, so for I, remember that it's rate over compoundings, is giving us 3%, so 0.03 over, And we are compounding semi-annually. So semi-annually would mean that this money gets compounded twice a year. So this would be 0.03 over 2. 0.03 over 2. Hey, I can work with that. 0.015. And then N is MT. And we're doing this twice a year for 5 years. So there's 10. Okay. And since we're solving for P, remember that this is the formula we're using. P equals A over 1 plus I to the N. Okay. So we want to have $20,000 in the future over 1 plus I, which is 0.015 raised to the 10th. Okay. Let's see. 20,000 over 1 plus 0.015, all raised to the 10th. And in order to have $20,000 in 5 years at 3% compounded semi-annually, you need to invest $17,233.34. Eel. So you want to put that much money in, and in 5 years, you'll only make 20,000. So you'll make $2,800. Again, these are just examples. These are good examples of what we should not do. All right, everybody go with that. I was like, man, if you put in $17,000, you better have like double or triple that in 5 years. That's just me. Okay. 3. How long will it take $3,000 to grow to $22,000 if invested at 6% compounded monthly and then compounded continuously? So here we're going to use compound interest and we're going to use continuous compound interest. Okay. So when it says compounded monthly, we know that's the A equals P times 1 plus I to the N. And then compounded continuously, that's our best friend, PERT. Okay. But the kicker here, it says, how long? So we are looking for time. Okay. So for the first one, we'll call this A. We are looking for time. So time given by compound interest. Ooh, we made that formula all the way up here. Time is natural log A over P times N times the natural log of 1 plus I. Okay. So natural log A over P over M times natural log of 1 plus I. Okay. So for this one, they're giving us how long will it take 3,000 to grow to 22? So they're giving us the final amount, 22,000. They're giving us the beginning amount, 3,000. They're giving us the rate. Oh yeah. So if it's I, which is rate over compoundings, they're giving us the rate at 6% and compounded monthly 12 months in a year. Now, is that something nice? 0.06 over 12. Very nice. 0.005. And compounding, so all we need to know here, since there's no real n value, because remember that n is mt, but we broke it up because we're solving for t. So here, compoundings is just 12. Okay, we're ready to roll on this one. So we're going to get the natural log of 22,000 over 3,000 over the number of compoundings, 12, times the natural log of 1 plus I, 0.05. All right, let's see. Fraction, natural log, parentheses, another fraction, 22,000 over 3,000 over 12 times the natural log, parentheses, of 1 plus 0.005, close. And in order for 3,000 to grow to 22,000 compounded monthly, it's going to take 33.29 years. Woof. Not bad. But I would want more over a span of 33 years. Okay. So that's if you compound monthly. Now we have to figure out if you compound continuously. So B. And we need that time formula for continuous compound interest. So that's what we made up here. Time, natural log A over P over R. Okay, well, this one's going to be a lot easier to plug into. They already gave us A, they gave us P, and we know the rate. This one's so much easier than step A. So this would be T equals the natural log of 22,000 over 3,000 over our rate 0.06. Let's see what we got. Fraction, natural log, fraction. Oops. 22,000 over 3,000. Close that, 0.06. And if you compound continuously, you will still make 22,033.21 years. Not much difference, huh? You shave off 0.08 of a year if you compound continuously. Oof. It's all about that rate. Okay. Everybody go with 3. All right. And then 4. How long will it take money to double if it is invested at the following rates? 6.5% compounded weekly and 4% compounded continuously. So again, this says how long. So we are looking at doing the same thing that we just did above. So A. It says we want our money to double. So it's not giving us a specific amount. They're not giving us any amount, but it says how long will it take the money to double? So they want to tell us that the final amount will be twice the original amount. So the final amount will be twice the original amount. Okay. And then I is rate over compoundings. So our rate is 6.5%. So 0.065. And our compoundings are weekly. So this says how many weeks are in a year. And we know that that is 52. And I don't think that's a good number. Let's see, 0.065 over 12, not 12, 52. Oh, it is a nice number. 0.00125. And again, we're looking for time. So all we need to know is that compoundings, which is 52. Okay, so time equals the natural log of A over P, but in this case, A is twice the original amount. So it would be 2P over P over 52 times the natural log of 1 plus 0.00125. All right. Inside, your P's would cancel, and you would just have natural log 2 over 52 times the natural log of 1.00125. Okay, let's check it out. Natural log 2 over 52 natural log 1.00125. And whatever money we had, if we wanted it to double at 6.5% compounded weekly, it would double in 10.67 years. Okay, and that is compounded weekly. If we compound continuously, well, again, we use that formula just like we did above. Natural log A over P over R. Remember that A is twice the original amount, so 2P. You would have T equals the natural log of 2, because remember, it's the same situation here. 2P over P becomes 2 over our rate, 4%, 0.04. So let's see. Natural log 2 over 0.04. And if you were to compound, if you were to compound continuously at a rate of 4%, your money would double in 17.33 years. Oof. So again, it's all about that rate. That shortens your amount of time, right? First one was 6.5% compounded weekly. Next one was 4% compounded continuously. So at a higher rate, our money doubles in a shorter time. All right. Everybody go with that? Okay. All right. Okay, last page, y'all. And this is about annual percentage yield, or like you hear in those car commercials on TV, APY. This is the truest percentage rate that you are getting on your loan or your investment. So if you ever wanted to calculate your APY to see if your rate is actually true, that would be something important for you to do. And this is how you would do it. Okay, so reading this, it says, which is further, 60 kilometers or 35 miles? We don't know unless we actually know those conversions. Well, 60 kilometers is 37.282 miles. So we see that 60 kilometers is just a little longer than 35 miles. So in order to compare interest rate, we need to convert them to the same units of rates per year. the simple interest rate that will produce the amount A in 1 year, as if it were compounded m times per year, is called the annual percentage yield, the effective rate, or the true interest rate. Your annual percentage year in terms of compoundings, like regular compoundings, daily, weekly, monthly, semi-annually, is given by 1 plus r over m to the m minus 1, where m is your number of compoundings. And if you were given an APY in continuous compoundings, it would be given by e to the r minus 1 when you compound continuously. This is the annual nominal rate, and it's the same as the annual rate R. Okay, so these formulas will give you the true interest rate of your investment or your loan, specifically on a house or a car, or I guess any big purchases, maybe even credit cards. Okay, so example 5. What is the APY for money invested at an annual rate of 3.05% compounded quarterly and 2.95% compounded continuously? So, all right, let's check it out. So for A, you are compounding quarterly. So we're using that first formula above. So things that are given are the rate, which is 3.05%. So 0.0305. And you compound quarterly, which we saw that there are 4 quarters in a year. Okay, so put it together. APY is 1 plus your rate, 0.035 over your compoundings, all raised to the number of compoundings minus 1. So let's see what the true interest rate is on this 3.05% rate compounded quarterly. So parentheses 1 plus 0.035 over 4, all raised to the 4th minus 1. And throughout the year, you are getting, let's see, 1, 2, 3, we'll include that extra 4 on there. So we're going to round that up. 0.0355. So your actual true interest rate that you're getting yearly is 3.55%. 0.035. Just making sure I typed everything right. %. So that is what you're actually being charged on your investment or loan throughout the year. 3.55%. Or throughout the whole year. Okay. And then B, check it out for compounding continuously. So all we need to know for this one is your rate. So your rate is 2.95%, so 0.0295. And the APY here is going to be E to the R, 0.0295 minus 1. And our true percentage rate compounded continuously, let's see, E raised to the 0.0295 minus 1 is 0.0299. And that rounded up 2.99%. Sounds like those car commercials. You'll get 2.99% APR on this new car. Okay. And that is annual percentage yield. So that'll give you the true percent of what you're paying on, again, your loan or investment. Okay. Whew. All right, guys. That was 3.1 and 3.2. So just reference these formulas, know these formulas, know how to use them depending on the problem, and just know how to work that calculator. All right. Other than that, we are done for today. Yes, it was a lot. I told you we had a lot to get through, but it's not bad. You have the formulas now and you get to use a calculator. So it's nothing too crazy. All right.